Okay, great. Thank you very much. Hello, everyone. I apologize that I'm not there in person. I was supposed to be in Europe around this time, but things didn't quite work out. And but I'm glad that I have this opportunity to give this talk remotely. And because of time difference and being remote, I haven't seen some of the other talks. So hopefully this wouldn't be too disconnected from the rest. So Freddie, is everything okay?
Yes.
Yeah, we're trying to get the sound a bit louder, but so if you can speak a bit louder, maybe on your side, I don't know.
Okay, great. Okay, I'll do my best. Yeah, so today I'm going to talk about some work we have been doing the past few years on using machine learning, particularly deep neural networks, for basically closure modeling of turbulent flows. And in today's talk, I'm going to discuss three specific aspects of this work that's about the stability, extrapolation, interpretation. And I'll tell you soon exactly what these mean in this context. Now, in this talk, I will be mainly talking about subgrid-scale modeling, but also I'll mention some work about spatial-temporal forecasting. I will be talking about a number of systems, 2D turbulence, QG, Rayleigh-Bernard, and atmospheric gravity waves as motivations for our work. And in parts of the talk, I will be discussing concepts from physics, like backscattering, and in some other parts, I will be talking about concepts from machine learning, like transfer learning. And at the end of the talk, I'll tell you about this recent work we have been doing on basically integrating Fourier analysis of neural networks and nonlinear physics, which is something I'm very excited about because it can allow us to address some of these questions about the stability, extrapolation, and interpretation more rigorously. I don't think I need to spend too much time on the motivation. We all know that there is a critical need for better extreme weather forecasts and climate change projections. And one of the most important tools, or perhaps the most important tools we need to do these, are more accurate and faster weather and climate models so that we can address these three major sources of uncertainty that we have in producing reliable climate projections. And also the first two, as you know, are relevant for weather forecasting. And again, here I want to emphasize that we need not just more accurate models, but also models that are fast so we can do long simulations and multiple simulations so that we can address these second and third sources of uncertainty. But as you know, simulating the climate system is challenging, and a major source of the challenge is that we are dealing with the multi-scale system. This cartoon here is just a reminder of a broad range of length scales and time scales that we have in the atmosphere alone. Of course, you can make similar cartoons for the ocean and other components of the Earth system. Now, for most applications, we actually want to predict what's going on here in the large and slow scales, but we can't ignore what's happening in the faster, smaller scales because everything is non-linearly interacting. Now, for many processes, we actually know to a good degree the equations, the often nonlinear PDEs that we need to solve, but we usually don't have the computing power to do that. For example, in a typical climate model that has a resolution of 100 kilometers, everything on this side has to be somehow represented. Now, as you know, the current approach, the traditional approach to this is to use a low-resolution numerical solver, basically a GCM, to resolve the largest scales. But to do this, we need these functions P, these are called parameterizations, that will tell us something about the smallest scales in terms of the large resolved scales. And there has been decades of work developing physics-based and semi-empirical parameterizations from theory and limited observations. But we know that to really improve our weather and climate models, we need much better parameterizations for many critical processes in the climate system. Now, very often we hear about clouds and ocean turbulence as examples of important processes that need much better parameterizations. So let me give you another example, and that's about gravity waves in the atmosphere. These are waves that are generated because of convection or interaction of the flow with the topography or fronts in the troposphere, and they go up in the stratosphere and mesosphere, and they break, and they drive the circulation variability. For example, they drive this important phenomenon in the tropical stratosphere called quasi-biennial oscillation, or QBO. These waves also affect the polar vortex variability and the resulting extreme events at the surface. The problem with these waves is that their wavelengths can be small. They might be just a few kilometers, as you see in these very high resolution simulations that we have done over a tropical region. But this is basically how a typical GCM would see these waves. It can't capture them. And as a result of these waves have to be heavily parameterized in the climate models, but the current parameterizations have a number of major shortcomings that I've listed here. And as a result of these, even the state-of-the-art climate models, including CMAP models, many of them can't even produce their own QBO, but also the climate change response in these models, even at the surface, can strongly depend on the choices we make for these gravity wave parameterizations. So clearly we need to improve these parameterizations, but the major question in climate science is how to do that. I should say that we can't just rely on the increase in the computing power because that's going to be incremental progress. The computing power is about to saturate, and also those very high resolution simulations are going to be very short. So we can't use them to really address those sources of uncertainty about internal variability or to do multiple simulations to address questions about climate change scenarios. So we need a different approach, something that would give us a giant leap rather than a more incremental progress. So as you know, in the past few years, machine learning has received a lot of attention as a potential avenue for doing that. There are many ways that machine learning can be used to improve weather and climate modeling. One approach is to just follow that traditional approach, except to replace some of those poor parameterizations with data-driven parameterizations that somehow have been learned from data. And again, there are many ways to do this. For example, we can imagine to replace some of the, to use machine learning to better estimate some of the parameters in the current parameterizations, or we can just leave it completely to a machine learning method like a neural network to learn the relation between these X and Y. Again, going back to the gravity wave as an example, I'm involved in a large international project called DataWave that is focused on developing new parameterizations for gravity waves in the next generation of climate models. You see that it's a big project with a lot of collaborators in US and Europe. So there's a lot going on here. What some of the work that my group is leading, we are building a library of very high resolution regional simulations, like the ones that's shown here. We have colleagues in Germany, Claudia Estefans, doing global, very high resolution simulations using ICON. And we also have observational data, especially from Google balloons. These are balloons that were used to provide internet, and by looking at the trajectories, we can estimate gravity wave fluxes. So one idea here is to combine these data sets plus what we know from the physics and to train neural networks to represent the effects of these small scale waves in a typical climate model. To give you a better idea of how this learning parameterization from high resolution simulations work, let's go to a simpler system, and that's two-dimensional turbulence. The equations are shown here. This omega is vorticity, psi is the stream function, this is the nonlinearity. The Reynolds number is a parameter that will tell us how turbulent the flow is, and we can have forcing and damping. Now, at a modest Reynolds number with high enough spatiotemporal resolution, we can numerically solve these equations without any further simplification. And we call that direct numerical simulation, or DNS. And in this work, we are going to treat that as the truth. Now, DNS is very expensive. It's not practical. So what's done in climate modeling and in many other disciplines in science and engineering is to do what's called large-eddy simulation, which, as the name suggests, it means that we are only going to solve for the largest scale features. So to derive the equations for LES, we can take these original equations and just low-pass filter them. And we know that when we do this, we can almost write these new equations in terms of just psi bar and omega bar, except that at the end, we'll end up with this term that we can't close. We can't analytically write this just in terms of psi bar and omega bar because of this nonlinearity. And this is basically the closure problem in turbulence. So I'm going to call this term pi. This is the subgrid-scale term. This is where the effect of the small features are. Sometimes you see these written in terms of those prime terms. And the Reynolds stress, which you might know about, is one of the terms here. Now, the computational advantage of LES is clear. We need much lower spatiotemporal resolution to solve these equations, but then we need a model for pi. We need a parameterization. And there has been decades of work trying to develop physics-based parameterizations. One of the earliest and still widely used models is the Subgrid-scale model and its variants. So the idea in these kind of models is that the smallest scales mainly dissipate the largest scales. So we can represent their effects with some sort of viscosity. But one problem with these kind of eddy viscosity models is that they're too diffusive, so they can't capture the extreme events. And you can see this even in this simple system. So here I'm showing you the PDF of vorticity. You can think of it as weather in this system. There's a black line here. That is the PDF of DNS. That's from the truth. And you see that the Subgrid-scale model and its more advanced variants, they're all basically can't capture the tails of the PDF. They can't capture the extreme events beyond 2-3 standard deviation because they're too diffusive. So one question is, can machine learning do any better? Can we, for example, train a neural net to find this mapping between the subgrid scale term and the resolved flow and actually capture the tails? Now, you might notice that there are results with the CNN here. That's a blue line. And you see that it perfectly matches this PDF, including at the tails at 5 and 6 standard deviation. So the answer is yes, but as I'll tell you soon, we had to address a major challenge to get this to work. Now, so far, I talked about one way of using machine learning to improve weather and climate modeling, which is to improve parameterization. But I also want to mention another direction that has received a lot of attention in the past few years, and that's fully data-driven modeling. So the idea here is to just forget the PDEs that we know, and we train a neural net to take the state of the atmosphere or ocean or whatever you are interested in at the current time and predict it at some later time, like a few hours or days later, and then we put this back and auto-regressively we march in time. Now, this kind of approach is very appealing because once trained, these models are cheap, so we can do real-time forecasting, we can do probabilistic forecasting, this can be used to improve data assimilation, or we can turn these into fast statistical emulators, which have a variety of applications. To give you an example about this kind of approach, there is a model called ForecastNet. That's a data-driven weather model. It's developed by NVIDIA and Caltech, groups led by Anima and Kartik, and my group and a number of other groups have contributed to this. I would say that these kind of models now have impressive performance. ForecastNet was trained on only 40 years of reanalysis data. But if you look at this paper, and now there are even better results, this model has accuracy for day-to-day weather and even some extreme events like hurricanes, atmospheric rivers, heat waves, that up to several days can be comparable to the best numerical weather model, such as the European model, the ECMWF model. But the issue is that the key point here is that these models are 100,000 times cheaper and faster than those kind of numerical weather models. So I would say that in the past few years, there have been a lot of promise about the applications of machine learning for weather and climate modeling, and there has been some progress. But really, to turn these advances into operational and practical advances, there are a number of major questions and challenges that we need to address. And this is mainly because what has been used mostly in the past has been basically the same architectures that have been developed for commercial and medical applications. For example, these data-driven models, they don't know anything about physics. For example, ForecastNet uses something from computer vision. As you can imagine, these can lead into problems. So just to give you some ideas of some of these questions and challenges, which I'm sure many of you are currently thinking about these or working on addressing them, and these are relevant to any kind of application. The first question is that what's that actually we want to learn? If we are supposed to find a cat, I think it's pretty clear what we need to learn. But that's not a trivial question about climate or turbulence data. For example, I mentioned before that we want to learn the effect of these small scale waves in these high resolution simulations and put them into these low resolution climate models. So basically, we need to be able to estimate this pi term in these high resolution simulations. But we just submitted the paper that we compare the three most common approaches to do this by doing filtering coarse graining, by doing things like Helmholtz decomposition. And we showed that you can actually get pretty different answers about what this pi term is. As you can imagine, there can be a lot of sensitivity to actually the details of filtering and coarse graining. Even once we know the pi term, then the next question is, what is about this pi that we need to learn? Is it enough to just learn the structure of pi, as pretty much all studies do? But it turns out that's just the first necessary condition to have a successful parameterization. The second one is to actually learn the interscale energy or entropy transfer. But as this paper by Charles Manevo showed nicely in the early 90s, we can actually never find the sufficient conditions for this. And as we try to find the sufficient conditions, basically more and more necessary conditions would show up. So basically the closure problem in turbulence would also show up when we try to find the sufficient conditions. Now, these are not machine learning questions, these are pure physics questions, but the answer have important implications for the choices we make for the loss functions and the metrics. Now, after this, we have to figure out actually how to do this in a small data regime, which is really what we are dealing with in our applications. We need to figure out what physics to include, how to deal with causality, which is an important issue. And Tom, and as he talked about it, he and his colleagues have been doing some interesting work about this. And certainly you can see the improvements you get out of accounting for causality, how to learn the rare events, and how to do uncertainty quantification for the predictions that we get from these models. And then I would say there are three problems that are the most challenging one, at least in my opinion, for climate applications. One is interpretability. We need to understand to some degree what these methods are learning and why. There is the problem of out-of-distribution generalization, or really extrapolation to a different system. like to a changing climate. For example, this is what happens when we expect a data-driven parameterization to extrapolate. We see that the simulation quickly goes unstable. I'll tell you more about this simulation in a few slides. And in fact, these kind of instabilities are very common in applications of machine learning to climate and turbulence data. And for example, those data-driven weather models that have very good performance up to several days, they all blow up when you go to several weeks of integration. So there are a lot of promises, some progress, but also a lot of challenges. And I want to argue that we shouldn't be discouraged. And I want to draw an analogy from the history of climate modeling. So the history is usually told as von Neumann and Charney and Subgrid-scale and others got together in Princeton and used the first digital computer to actually do the first numerical weather forecast. And then a decade later, Manabe and others built on this work and developed the first climate models. And then all these amazing science emerged from that. But we shouldn't forget that the first attempt to do numerical weather forecasts was done in 1910 by Richardson, which very badly failed. It was so bad that they never tried it again. And it was 20 years later that Grant and his colleagues who were developing rigorous methods for numerical analysis actually identified the problem in Richardson's work, which was the CFL condition. And still it took another 20 years for von Neumann to get his hand on ENIAC and do the first successful forecast. And in between, the atmospheric science had really two sides. One was that people were trying to do data science, doing everything by pattern matching. And the other side, led by people like Rossby, that people wanted to do reductionist science and use the first principles and the PDEs, except that they really couldn't solve them. And if you look at the history, there were actually a lot of feud between these two sides, and especially between Rossby and Craig. So the point I'm trying to make here is that the success of climate and weather modeling, the numerical climate and weather modeling that we have now, it actually required decades of progress in several different disciplines. And in getting there, in particular, I want to emphasize the importance of the development of these rigorous frameworks for numerical methods. So in my opinion, with machine learning for climate, we are currently here, except that this time we are not going to abandon one approach in favor of the other, but this time we are going to combine them. Basically, we are going to combine this reductionist science approach that we are all familiar with the approach based on the machine learning and particularly the neural networks, because they really have complementary strengths and weaknesses. Reductionist science, as you know, if you have developed a good theory, you can fit like one parameter and it would tell us how apples would fall on Earth, on Jupiter, or on an exoplanet that we might not even seen. So these models are very generalizable and interpretable, but they can be very slow to develop for very complex systems. And on the other hand, these overparameterized neural networks, they are very expressive. They can learn pretty much any function if there is enough data, but then we know that they're poorly generalized and they're hard to interpret. And of course, you have heard this kind of document from many people, this kind of argument from many people like Tapio Schneider and others about the need for really combining these two approaches. So we are going to really try to combine the tools that we have, the mature tools that we have that we have been using for reductionist science, using theory, model hierarchies, and observational data, and really combine this with this progress in the machine learning community to develop scientific machine learning or really climate science machine learning. And I think by doing that, we can make more progress and address some of those challenges. And in doing this, again, I want to emphasize the importance of developing rigorous methods. So to contribute to these efforts in the past few years in my group, we have been developing a hierarchy of test cases that goes from simple systems like Lorentz to canonical turbulent flows all the way to climate and weather data. And we have been basically using this the way that we use climate model hierarchy. We identify questions and challenges here. We go to simpler systems to understand what's going on, maybe develop some methods, and then we go back to make sure that everything is scalable, which in my opinion is extremely important. So to give you some examples about work that we have been doing using this hierarchy, we have been looking at some of these models to understand the sources of these instabilities that many people have been reporting about using machine learning for subgrid-scale modeling. So in the work that I'm going to discuss, we have been training a convolutional neural networks to basically develop a spatially non-local parameterization. So basically the input to these CNNs are snapshots of the LES state and the outputs of these pi terms that we can go and diagnose from the high fidelity data like the DNS data. As I mentioned before, this is actually not a trivial task, but for now, let's say we have done this right. and we have the true pi term. We have tried to keep this architecture as simple as possible, but I emphasize that we have been developing a non-local parameterization. So we take information from the entire domain or large parts of the domain as the input because we think that's important. So just to introduce the notation that I'm going to use from now on. So as you know, this is the equation for a CNN. This G, this is called activation. So this is the output from a layer and a channel. Here it's 128 squared matrix, the same size as the input and the output. These W's, these are called kernels. These are basically a small 5x5 matrices that do convolution on the activations from the previous layer, as shown here. These kernels are the main things that we learn when we train a neural net, when we train a CNN. So there are 5x5 matrices. There are around 4,000 of them per layer. There are 10 layers, so we have a million learnable parameter in this network. Everything is linear here. At the end, we have a nonlinear function. So we learn these weights and these a small number of biases, and collectively I'm going to call them theta. Basically, we do this by minimizing a mean squared error loss function using n training samples. Now, as much as neural networks are called black boxes, the math is actually not that complicated. But what makes them look like a black box is that it's hard to know what they have learned and why. For example, this is one of those 40,000 kernels that we have learned in this work. And it's hard to look at this and see anything meaningful. But in a few minutes, I'll come back to these and I'll tell you what these and all these other kernels are. So once the CNN is trained, now for unseen samples, it can basically predict pi. So we can couple it to the LES solver and do a simulation. This is called offline learning in climate community because we train the CNN and then we coupled it. And of course, this is supervised learning in machine learning language. But as you can imagine, online learning would mean to train the CNN while it is coupled, and that approach has its own advantages and disadvantages. Okay. Is there a question?
Just in space, or is it because learning in space and
yeah, that's a good question. So here we are just doing coarse graining in a space. So we basically take a snapshot of psi or omega or any variable in a space. It's a snapshot in time, and then we filter it and then we coarse grain it. And those would be the overbars. And out of that, we can also calculate the pi term. So we are not accounting for any memory in this parameterization. So as I mentioned, we have tried to keep this very simple. So there is no stochasticity, there is no memory, and we wanted just to keep things very simple. Okay. So like many other people, we also found that we can train a neural network on DNS data, and we get a neural network that looks pretty accurate based on the common physics frame metric, that's pattern correlation. We can have pattern correlation like 0.95 or even 99. But then we couple these neural networks to the LES solver, they blew up. And so at this point, again, many other people have also found similar results in climate models, even in these kind of simple systems like 2D turbulence or 3D turbulence. And many others started thinking that, well, there could be a major flaw in this offline learning approach. Maybe the estimates of pi are very bad. Maybe the numerical errors are causing issues. Maybe we must have a stochasticity, or maybe we must have memory or something else for this approach to work. So in this paper, we actually went back thinking about the physics a bit more. As I mentioned before, we know that the smaller scales are doing diffusion. They dissipate the larger scales. But also we know that the smaller scales, local in a space and time, they can actually do what's called backscattering, which is really a forcing on the larger scales. You can think of it as anti-diffusion. So when we switched our metric to something that was focused on backscattering, we found that backscattering was actually not learned very well. Basically, it was poorly learned. And this is basically a data imbalance problem. It turns out that large backscattering is rare. So if you don't have enough data, it's not going to be learned well. But backscattering is a forcing on the flow. So as you can imagine, it has been poorly learned. It can cause problems with the stability. So what we did here, we just increased the amount of training set, the training data we had. This number got above 0.9. And then we saw the power of this CNN. And we got the results that I mentioned to you before. That would be the blue line. that you see that this CNN can now capture the tails of the PDF very well because it has the right amount of diffusion and the right amount of backscattering. The physics-based models like Smogorowski, they basically are too diffusive, and a big part of their problem is that they actually don't account for any backscattering. As you know, backscattering is a real phenomenon. It can be important in many type of turbulent flows, not just geophysical turbulence, but also in engineering turbulence. And there has been a lot of work on this. For example, Freddie has done a lot of nice work on backscattering. And there have been efforts in trying to include backscattering in parameterization of oceanic and atmospheric or engineering turbulence, but it always caused issues with instabilities. But with enough data, deep learning can capture it well. But of course, expecting a lot of data is not practical. So now that we know the physics that mattered, in the next paper, we included that physics and more into the training process. And in this newer paper, we showed that actually now with a much smaller amount of training samples, we can actually get the same performance from the CNN. In this paper, we did a few things. We included equivariances and things like that. But one thing that we did, and it helped a lot, we basically included that second necessary condition into the loss function as a regularization term. So basically here we have included interscale entropy transfer domain average as a regularization term here, and this on its own helped a lot in reducing the amount of data that we needed to get a stable and accurate simulations. So now the next question is, well, can these neural nets extrapolate? So here I'm showing you results that basically we trained the neural net, it's same CNN, on the Reynolds number of 8,000, and we showed that it can work pretty well for the flow for the Reynolds of 8,000. It captures the spectrum pretty well. But then if we tried on a flow that has a Reynolds number of 64,000, we get this red line. We see that it starts to curl up. If we continue this simulation, this is going to blow up. So the answer is no, and this shouldn't be surprising. None of these neural nets should be expected to, or any other machine learning method should be expected to generalize out of distribution, to extrapolate to a new system. And of course, this is well known in the machine learning community, and they have a solution for it that's called transfer learning. Now, before showing results for transfer learning, let me also show you another set of results about lack of generalization. This is more impressive when you look at a Rayleigh-Bernard convection. So this is a Rayleigh-Bernard convection at a Rayleigh of a million, Rayleigh number of 1 million. This is at Rayleigh number of 40 million, much more turbulent flow. And if we train a CNN on this, and then we expect it to work on this, we get this unstable simulation that I showed you before. Here we are doing basically parameterization for both heat and momentum. If we do transfer learning, then we get this last simulation where you see that everything is stable, it produces the statistics correctly. And for example, if you care about the heat transfer, the Nusselt number is captured well. So many of you probably know about transfer learning. It's basically the idea is that if I have a neural net that's trained for one system, and if I have data from a new system, if I retrain this neural net, just parts of it, even like one layer, with this new data, if this is done right, then this network is going to work for this new system. To basically explain this with some cartoons, what we have done so far, we have taken n random samples from a system, and we trained a CNN from scratch when everything was randomly initialized. Now we want this to work for a new system, a target system that might be different because of a different Reynolds number or different forcing. So the distribution is different. But let's say we don't have another n samples, a large number of samples from this new system, but we have a small amount, like 1%. So what we are going to do is that we are going to freeze everything except some of the layers, could be even 1 or 2 layers, and we are just going to retrain these. We are going to update these. And the machine learning literature generally suggests to retrain the deepest layers to get the best performance. And we started doing this for Lorentz system, and everything worked well. And then we tried it on this 2D turbulent flow, and we got results that, again, it works pretty well. So here, same example as before, we took the CNN that was trained on this system. We retrained just one layer with 1% data from this high Reynolds number, and then we got this dashed red line, which you see that it works pretty well. It's basically as accurate as if we had a large amount of data from the new system. So by thinking about physics and by using some of the machine learning techniques, we can actually address some of these questions about a small data regime, the physics, even extrapolation, and stabilities. Still, by doing this kind of work, we don't have interpretability. And still, I mentioned that, for example, in transfer learning, we need to do retrain the right layer, but then the question is, what is the right layer? Currently, a lot of things are done based on try and error. So that's where really the need for the kind of rigorous frameworks that we have for numerical analysis comes in, that we really need to start developing such kind of approach for these kind of applications. So in our group, we started thinking that, well, when you study climate data or turbulence, very often we look at our equations or data in the Fourier space or in other kind of spectral space, because this is where the math and the physics might simplify and we can better connect basically with our theories. So we thought we'd just do the same thing to these neural networks. So going back to the equation for a CNN, we can write down the Fourier transform of the activation analytically. To do that, this blue part, this is all linear. I'm going to call it H. Remember, there is a convolution operation here. I'm going to use the convolution theorem and basically get the H hat, which is the Fourier transform of H, which basically becomes, this is now a element-wise multiplication between the Fourier transform of the kernel and the Fourier transform of the activation. Now, even though there is a nonlinearity here, that's a real U, I can still analytically write down the Fourier transform of G. Basically, I'll get this sum that comes from the nature of real U. This is basically the Fourier transform of the Heaviside function of H. So basically, this tells me that the Fourier transform of an activation from a layer to another layer, and eventually from the input to the output, it depends on this sum, but more importantly, it depends on the Fourier transform of the kernel, which basically suggests that instead of looking at these kernels in this physical space as 5x5 matrices, we should look at their Fourier transform. Remember that these are doing convolution on 128 squared matrices. So I'm going to pad this to 0 to 128 squared and then do 2D FFT. When I do that, I'll get this. So here the x-axis, this is wave number in the x direction, wave number in the y direction. We see that this kernel was basically a low-pass filter. It's basically 0 everywhere except for this blob at the center. So we did this for all these 40,000 kernels. And then we saw that in the Fourier space, a lot of these kernels looked very similar. So we just came in clustered them. So here what I'm showing you for 3 different CNNs that were trained to do subgrid-scale modeling on different systems, I'm showing you the cluster centers of the spectra of these kernels. And this is for layer 2, layer 10. We see that generally there are a lot of similarities in what we have learned between different layers and even different CNNs. We have learned a lot of low-pass filters. We have learned high-pass filters. And also we have learned these filters. These are interesting bandpass filters. And these are just Gabor filters. So basically, if you take a sine function, multiply it with the Gaussian, you get these kind of wavelets, and this is their Fourier transform, which basically picked out these wave numbers. So basically, now I can tell you everything these CNNs have learned. Basically, 1 million learnable parameters turned into a few classes of low-pass, high-pass, and Gabor filters. Now, I should say that it has been known in the machine learning literature that CNNs can learn Gabor filters and more broadly wavelets. There's been beautiful work by Stefan Mallat, John Bruno, and others showing this. And even beyond the machine learning literature, in the neuroscience and sparse coding literature, there have been a lot of nice papers showing that if you are trying to learn multi-scale localized oriented features, which is the kind of data we have in turbulence and generally in climate, these are actually the basis functions to use. And the key to learning these would be a sparse learning where neural networks can, over-parameterized neural networks can do through implicit regularization. So the point is that there's actually a lot of nice work in the other communities that we can leverage here. But as far as I know, this kind of analysis has never been done for applications of neural networks to dynamical systems. But I find this pretty exciting because now we can start thinking of maybe we can develop some skeleton models or reduced order models for these neural networks completely end-to-end in the Fourier space, because here we can think about exploiting some of this sparsity and redundancy that we see. Notice that even though we are trying to learn a system that doesn't have clear scale separations, when we look at these Gabor filters, there are very specific wavelengths that they are picking out. They're not picking out all sorts of wavelengths, but there are very specific wavelengths that they are picking out. And so this is basically, there is a lot of sparsity in the Fourier space. So anyway, this is work that we have just started thinking along these directions. Of course, we are not there yet. There are 10 layers and the nonlinearity between them. So it's not still very simple, even if you have a sparsity, to really simplify the model, to have a skeleton model. Is there any question or? Okay, but Fortunately, for transfer learning, we can already make more progress because transfer learning is all about changing one layer or two. The results I showed you, they're actually in the appendix of this paper that just came out, because this paper is focused on transfer learning. And I should say that this is work that was led by Adam Subel when he was an undergraduate student at Rice. So in this work, we basically played with the Reynolds number and the forcing on 2D turbulence, and we created 3 cases. Each case had a base system and a target system. Here, the base is decaying turbulence, the target is forced turbulence. In this case, we go up 2 orders of magnitude in Reynolds number, and in this case, we change the forcing wave number. So basically, as you see, we have created very different flows, whether you look at them visually or if you look at the spectra of the flow. One thing to remember is that when we look at the spectra of the pi term, the main difference between the base and the target systems, the main differences are in the large scales. Now, long story short, in this paper, we showed that here, if you do not do transfer learning, you cannot go from the base system to the target system. If you do transfer learning, then it works. But also, we did something else. We looked at all combinations of 1, 2, 3, 4 layers to retrain. And then we found something interesting. In these 2 cases, the shallowest layer, layer 2, was actually the best layer to retrain for transfer learning. And in this case, layer 2 was doing most of the work, and adding layer 5 was making that the optimal one. Now, this is opposite of what the machine learning literature suggests, which is to retrain the deepest layers. Here, we actually found the shallowest one to be the best. In this case, for example, retraining the deepest layers, 9, 10, or a combination of 9 and 10, actually don't get you anything with transfer learning. So we start thinking that, well, can we understand actually what's the physics that learned during transfer learning? Can we a priori predict what would be the optimal layer? And can we use some of this knowledge to actually reduce the amount of data that we need for retraining, because that's the most precious thing in transfer learning. So we applied this Fourier analysis to this. The first thing we found is that even when we retrain one layer, out of the 4,000 kernels, only a few change. So we are in some sort of lazy training regime. Here, what I'm showing you is that I'm showing you the kernels of the 4, I'm showing you the spectra of the kernels that change the most during retraining. These are the top 4. So this is for case 2 and case 3. We see that basically in transfer learning, kernels that were not doing much, they were turned into low-pass filters when we did transfer learning. And this makes sense because remember that the pi terms in all these cases, they mainly change in the larger scales. So basically transfer learning said, I've been shown new data that's different from my old data in the larger scales. So I'm going to learn a bunch of low-pass filters to learn this difference. Now, layer 2 can do this. Layer 10 can't. These are the 4 kernels that change the most during transfer learning if we retrain just layer 10. And we see that basically kernels that were doing something or nothing were turned into some other kernels that are clearly not low-pass filters. And if you are at layer 10, and after that there's just a linear layer, a linear activation, then you really need to learn low-pass filters if you want to capture changes in the larger scales. Now, I can't tell you why layer 2 can do this and layer 10 can't, and I don't think there is general theory for this, but we found that there is some nice recent work in the machine learning literature about the use of looking at the loss landscapes to guide to explain transfer learning, and we can use it to guide us here. So I'm not going to go through the details, but the idea here is that we basically perturb the weights of a trained network in random directions. We reevaluate the loss using the new data, and we plot the loss landscape. And if the loss landscape is flat and smooth, then this is a good layer to retrain. If it's not, this is not a good layer. And here I'm just showing you 2 examples, but we have not done all of these analysis that I'm talking about for a few other systems like quasi-dystrophic turbulence and Rayleigh-Bernard. And we always found the answer of the optimal layers to be consistent with this loss landscape analysis. It's not that always layer 2 is the best. Sometimes the middle layers are the best, but we always find it to be consistent with the loss landscape. So now we have put these ideas together to build a framework that can be used to optimize and explain transfer learning, generally for applications in dynamical system. So the idea is to start by comparing the spectra of the data of the 2 systems. The loss landscape would tell us what layers would be the best to retrain. Once we do that, we can look at the spectra of the activations layer by layer and the spectra of the weights, and these can be connected back to the physics. And then there are a number of natural next steps in this, in trying to use this knowledge to even do transfer learning more efficiently and to combine this also with pruning, whether to guide pruning or to understand, for example, during pruning, which of these kind of kernels are actually the ones that are removed. So these are some of the work that we are currently pursuing. Now, we are excited about this because this kind of framework can be useful. For example, we are going to use this in our gravity wave project to deal with climate change. But also, I should say that transfer learning, as you know, is a very powerful tool, not just for this extrapolation problem in parameter space, but also to combine data sets that are very different. For example, if you have a large amount of simulation data and a small amount of observation data and you want to use them to train something, transfer learning would be the way to do this. And for example, we are going to use this to combine the balloon data with our simulation data. And the balloon data are not even going to be gridded, they are going to be sparse and noisy. Okay, basically, by doing this Fourier analysis, I think we can make more progress in terms of interpretability and developing rigorous frameworks that can closely connect physics and the deep neural nets together. But of course, this is at the beginning stage, but I think that can be a promising direction, combined with a lot of other interesting work that's going on in different communities for a similar purpose. Now, because I think I have a couple of minutes left, let me also mention that what I talked about so far was just one way of using machine learning to improve subgrid-scale parameterization, which is the offline learning using deep neural nets. But of course, there are various ways to do this, and there are many ways to even categorize these different approaches. So here I have categorized these approaches based on the use in terms of interpretability. On one side, we have deep neural nets that generally believed to be very hard to interpret. And on the other side, we have these equation discovery techniques that are now receiving a lot of attention because at the end, they hand you equations. And there has been a lot of nice work applying these to systems that we know about and recovering the equations that we know. But also there has been some nice work, for example, especially by Lorzana, applying it to a problem that we really don't know the answer to, which is the closure modeling. But I wanted to put these next to each other because I think these approaches, they both have their strengths and weaknesses. I think the equation discovery methods are also not the kind of crystal ball that many people think they are. There's a lot of sensitivity to how we choose the library or enforce a sparsity. And things like that. But again, I think really we need to combine these kind of approaches and try to push in both directions. But then for each of these approaches, there is a way of doing offline learning that I talked about, but also online learning. And in online learning, as you know, there's a lot of interest in recent years. There's a lot of nice work by Tape Schneider's group on using ensemble-Kalman inversions to do these, some work on reinforcement learning. Our group has been doing some work with a method that's very closely based on data assimilation. And also, as you know, there's now a lot of interest in differentiable modeling. There's been some nice work from Julian and Ronan's group on using differentiable modeling to learn subgrid-scale parameterizations for similar kind of systems that showed very promising results. So I just wanted to mention this, that there are many ways to make progress, and I think the ways that we choose at the end would depend on the specific application. Okay, but here I only talked about this one specific direction. Okay, so to wrap up, this is just a summary. So I discussed that we can develop a stable and accurate parameterization by offline learning. It might be data hungry, but we can address that to some degree by including physical constraints. And then the problem of extrapolation can be addressed by using transfer learning. Of course, as Tom mentioned, for problems that you can address that by doing like a scaling or things like that, or you know enough about the physics to do that, then that's certainly the way to go. And also those can be combined with transfer learning. But transfer learning is a very general way of addressing the problem of extrapolation, but of course it needs some data from the new system. Another thing I want to emphasize is that there's a lot of discussion about discrepancies between offline and online performance, and also offline and online learning. And I think, again, offline and online learning, I think they're both interesting, and we should pursue both directions. But I also want to emphasize that offline learning certainly can lead to stable and accurate parameterizations. And regarding the discrepancy between the offline and online performance, I think that's really something that depends a lot on the metrics that we use and the loss functions. And as I mentioned, by thinking more about the physics, we can actually come up with loss functions and metrics that are more physics aware. And there, the evaluation on the offline performance, I think, can be very informative about the online performance as well. And finally, this following this spectral analysis direction, I think, can help us developing more rigorous methods. I showed you results for parameterization, but also we have been now using these to address those questions about why these data-driven weather models and similar data-driven models for turbulent flows goes unstable. And by doing Fourier analysis, we can actually see the reason and come up with solutions for it. So with that, I stop here, and I look forward to your questions.
Thanks a lot, Pedram. Are there questions here in the room or online? Online, do not hesitate to post questions in the chat.
Are there questions?
I may start, Pedram. Yeah, regarding the analysis of the transfer learning, where you understand that experimentally you've seen that, or you saw that it may be better to retrain or fine-tune the shallower layers. So I was wondering, I assume that in the deep learning literature, most of this type of analysis may have been performed for classification models, for which we interpret the deeper layer more in terms of large scale and possibly semantic concepts. And then we expect the first layer to relate more to low level signatures. I was wondering whether you've been exploring whether for image processing issues like super resolution in painting, people have looked at similar analysis as what you've done. And maybe the result would be different, and also maybe for super resolution and generalization properties, you might expect maybe similar results for the one you got.
Yeah, that's a great point, and I should have mentioned this, that I think the reason for this discrepancy comes from the fact that what's in the machine learning is mainly about classification problems, right? And here we are talking about a regression problem, but also there are some differences in the network architectures. Like here, we don't have pooling. And one reason is that we and other people have found that if you include pooling when you do parameterization, actually the performance would be degraded. I think part of it is that it actually induces some invariances that's really not in the data. But yeah, you're absolutely right. I think it's really about the difference in the application, and we should look at the applications in the machine learning community, like super resolution, and there the answer might be different. I think it's some work to make sure that you are doing a fair comparison. Like every time you retrain a new layer, you have to do the hyperparameter optimization and things like that. So it's some work to really get the answer to for a specific data and architecture, which layer would be the best. And really, the place that you really see a difference would be when you have a very, very small amount of data. But yeah, certainly, I think that's something to look at. One thing I want to mention along these lines is that in the machine learning literatures, people generally find that the shallower layers learn Gabor filters. And as you mentioned, that's because people think we are learning the general features in the first layers, but not in the deepest layers. They don't find Gabor filters. Here, you see that we have a lot of similarities in actually across the layers. Layer 1 and 10, in terms of the cluster centers, are not that different. Of course, these are cluster centers, so they smear out a lot of details, but that's another difference, is that here, across the layers, we actually learn similar filters. So that's why we are interested in pruning, to see that when you do pruning, what are the layers that actually, what are the specific kernels that would be removed, and whether there would be a difference across the layers.
Thanks a lot for this answer. Said, you had a question online. You should be able to unmute and raise your question to Pedram.
I can unmute. Can you hear me?
Yes.
Okay, thank you. Thank you. Very nice presentation. I was wondering whether you encountered some instabilities that were due to the numerical solver when you were plugging back your closure into your numerics. Does it do some kind of? Did you have some issues in there? And I was wondering if there is any, can you actually disentangle between those and actually instabilities that are truly due to missing backs or missing or mismatching in the backscattering of your model?
That's a fantastic question. I think that is something really important to think about and develop methods to actually be able to quantify the contribution from each. So here, once we address the problem with a small data regime and learning backscattering enough, we got a stable simulations. So in this case, the numerical errors didn't seem to cause problems. Here we are using a pseudo-spectral code for some methods that might have basically more numerical discretization errors. That might be an issue, but I certainly agree that that is a problem. Even frankly, whether you are predicting the stress tensor or its divergence, I think it would matter, because something I didn't talk about, but spectral bias is a major problem in using machine learning, like deep neural nets for kind of turbulent flows or climate data. So spectral bias is the problem that the neural networks can't learn high wave numbers, high frequencies. So you can imagine if you are learning tau and you are not learning the high wave numbers and you take this divergence, then you are going to get bigger errors compared to if you were just learning the divergence of psi directly. So even that kind of detail, I think, eventually can be important and something to be careful about. But back to your question, I think it would be very important to develop methods that we can use to quantify how much of an error comes from numerics, how much
Sources of errors,
from epistemic error of a neural network itself, and then how they interact. This becomes a major problem when you are doing a spatiotemporal forecasting. Again, I didn't talk about it, but that's basically why these data-driven models go unstable, because you are doing autoregressive integration, right? So every time you generate some errors, right, and you put it back, and there are errors that come from the way that you do integration. So I think in the next few years, that would be like one of the interesting areas to think about.
Thank you. Thanks a lot.
Another question? Bertrand, you... Okay, I may have another one. I was really interested in the Fourier analysis of the network. That's really interesting. I understand but that's this slide, for example, and you focus on the spectrum, the magnitude, the amplitude of the spectrum. Have you also explored phase analysis in the spectral domain? And probably because we expect that the phase information is probably key to the backscatter, this kind of thing.
Yeah, no, that's a fantastic point. I think that's something important to think about. I mean, if you think about the current CNN, I mean, it has 10 layers and a linearity between them and 1 million parameters, right? So it's a little hard to just look at that directly and understand interactions. I think the first step would be to develop a skeleton model, a model that is simple. And there we can start thinking about this question. So Stefan Mallat and John Bruno have this whole thing, the scattering the wavelet scattering method, right? So I think like those kind of approach could become very helpful when you are going to learn some smaller models that you know more about what you are learning, still in the spirit of what the CNN is actually learning. And there, really, if we can understand the interactions from even like the applications of one specific kernel to another, and understand how much the phases would be affecting, and like how backscattering is learned versus diffusion. But I think it would take some time to make progress in that direction. But I think really like that is like a fantastic point that you brought up, and these are the kind of things we need to think about.
Okay.